So let me start by recalling a couple of definitions from last time that at the end of last class we were talking about. So for any x, any operator x, this is a good we define the left support and right support as those larger projections which if we multiplied by that side they behave like identity for that operator. Okay. So I first want to observe so this we've seen that the range of this thing is kernel perp of x and similarly the range of Lx is the kernel perp of x star, and one knows that Rx equals Lx star, right? That is clear from the definition. And so it is the same thing for x star, and so I can think of this as range x closure, or I can think of this as range x star closure. And this is kernel perp of x star. There are different ways of saying the same thing. Okay, and just one more little thing, maybe I observed this before, but see, for any x, I want to say that kernel x equal to kernel of x star x. Right? Because you can see that xi is 0 means that xi norm squared is 0, the same as saying x star xi is 0. But then you can take the square root of that x star x and push it over to the other side. And so you can see that actually kernel x star x power half, and that is the same as kernel of x star x. In general, for any positive operator A, the kernel of A and the kernel of A power half or A squared are the same. Okay. Definition. An operator P in B of Hk is called you all know what an isometry is, right? We've discussed this long ago. So to say that an operator is an isometry means that A star A is identity, right? Okay, so not P, let me call it V, not P. An operator V is called a partial isometry. So I will you use abbreviations like PISOM or PIS as the case may be. If it is a partial isometry, so that means there is isometry on a part. So what does that mean? See, you know that an isometry can never have kernel, right? Because it is non-preserving. The only thing it can kill is the zero vector. But partial isometries are allowed to have kernel. So the requirement is that V restricted to kernel perp V is an isometry. It is allowed to kill some vector, but on the complement of that it should be isometry, right? Example, the usual example, a good example to have in mind is something like an operator like that. It kills the first basis vector, but on the second basis vector it preserves the norm, sends it to the first one. Okay. So I want to say that is, so what is kernel perp of V? We've already seen that there is the same as kernel range of kernel perp yeah. So this is what this is same as kernel perp of V is same as range X star closure. We've already seen range V star closure. Or kernel perp of V. So this is just on a range of RV. Right? RV was kernel perp V, right symbol. So this thing called repeatedly. So it is good to use coin a word for this. So I will see this kernel perp V for such a partial isometry. It's called, by definition, this is called the initial space of V. There is one piece on which is isometric, the other piece is zero. That is the uninteresting piece. So the initial space of a partial isometry is the orthogonal complement of its kernel. And we will also use the same thing. We'll talk about the initial projection of V as a projection onto kernel perp V, right? Which we've already seen is RV. Okay. Okay. So let us, the next lemma kind of outlines some basic properties of partial isometries. So lemma let V and B of HK then the following are equivalent. V the partial isometry. Let me say with initial space equal. I'll use this notation for both the initial projection and the initial space. There shouldn't be any confusion. Suppose the initial space is I denote by M. To V star V is the projection. Actually equal to the projection onto M. Third, V equal to V star V. Okay. So I leave some space here and then head on the proof because there will be some more that I will add to that list. Okay, so okay, so I need to show, so let's prove 1 implies 2. I want to show V star V is a projection, in fact projection onto M. Then, so to say that V star V is a projection onto M, I have to show that it is identity on M and it is 0 on M pub. Right? So, xi in M pub or M pub equals, because you assume it's a partial isometry, that is equal to kernel of V. Right? Okay, so which is equal to kernel of V star V. And on the other hand, you notice that xi in M implies that what should I say? V star V xi equal to norm V xi squared, which is norm xi squared, equal to Pm xi xi. Okay, so what is this? This shows that the quadratic forms of Pm and the quadratic form of V star V, see, quadratic forms are continuous, right? And they agree on a dense space. See, this is so what we show is that they are equal on, first on M pub they are equal, and on M. In fact, because so no, I did not the correct, the clumsy way of saying it. So what do I want to say? I want to say that norm P M okay, but no, Z is in M, Psi is in kernel V perp. That means that this is equal to norm Psi squared. Because this is norm B Psi squared and B is an isometry on M. So, if norm P Psi squared equals Psi squared, norm Psi squared, last time I also should observe that if you have a projection, to say that it fixes a vector and that the norm is fixed. To say norm Psi equal to norm P Psi and saying P Psi equal to Psi are the same for a projection P. That means this says that Psi is in so P Psi equal to Psi. Why am I being so clumsy? So
on M part it is same and M it is also same. So M part union.
Why is the same on M?
On M it is the quadratic form is same. This time V Psi comma Psi equals to Pm Psi Psi. That means this time V minus Pm Psi Psi equals to 0.
So on M it is the same.
On M it is the same.
Okay.
And so then Z it is same.
What is it then said?
M part union M.
That is not done.
Of M part plus great sum M.
No, but Q is not additive. One is not saying the obvious thing. So V star V Psi yeah, actually what I should have done is the following thing. If we take
Sir, actually this V star is self-adjoint. V star is self-adjoint.
Yeah.
And this is 0 on the kernel of V.
V star V is 0 on the kernel
Kernel
of
of V.
Okay.
And on kernel of Earth, this is non-preserved. Because V star of Psi is
On kernel above, V is non-preserving, not V star.
And V is partial isometry you are using.
Yeah.
So V norm of V Psi is norm Psi on kernel of V. So this is the definition of.
No, but how do you conclude that V star V is equal to Pm? Why is V Psi equal to V star V Psi equal to Psi? star v xi let me try again. So v star v xi, let me do it this way. Let's take any xi eta in the Hilbert space. Then notice that v xi v eta equal to, see, v is equal to v times p, that is clear. Is it clear that v is equal to v times p? See, on the complement of orthogonal complement of p, v is identically 0. So in order to see what v does to any xi, it is enough to see what it does to p xi. So v xi is equal to v p xi. So v equal to vp, I'm drawing that v equals vp, and p v xi. I'm sure, I know the proof is really easy and straightforward. So you must be able to come up with it. I'm having some mental block.
I'm not understanding what is the wrong in that proof. V star v xi comma xi is to non xi square equals to xi comma xi. Inner product of xi comma xi.
Sorry?
If xi belongs to M, then v star v xi comma xi equals to inner product xi comma xi. So v star v minus identity xi comma xi equals to 0 for all xi belongs to M.
V star v
Xi comma xi equals to non xi square. Equals to means on M v star v xi equals to xi, and on
but why does
in the
v star v leave m invariant?
But there P is partial isometry on kernel of V, but P is isometric here. So V xi square is xi square here. On kernel of V.
If norm v square equal to norm z square, why is v star v equal to identity on m?
M is closed also.
Okay, so what is the argument? So clearly,
A is equals to M plus M part.
each equals m plus m pub. Okay,
On M, v star v, M part, v star v is 0.
okay.
So if you write any vector
On m, why is v star v equal to p? I want to know.
on M, v star v is xi equals to xi.
How do you know that? That's what we are trying to prove.
On M, v star v xi comma xi equals to xi comma inner product xi xi.
Okay,
So v star v minus identity xi comma xi.
but who told you v star v is an operator on m? Is it clear that V star V leaves M invariant? So what is the range of see what is the range of V star V?
Contain on range of these.
Huh?
Contain on the range of V star flow.
Range of V star V is range V star close. So we did that before. See, the range of V star V that's why I want you the correct thing. See, what is the kernel of V star V? We know is equal to kernel of V. So range of V star V, because V star V is self-adjoint, is the perp of kernel V. Okay. So the perp of kernel V is what we call this R of V. So V star V, range V star V is kernel perp of V, which is M. Forget all this. Range of V star V is kernel perp of V, which by definition is equal to M. That means V star V lands in M. So V star V can be thought of as a mapping from M to M. And once you view it as a map from M to M, that means V star V times the projection onto M is an operator in M, B of M. And what this thing shows is that this and PM, this can also be viewed as an operator in M. They have the same quadratic form. See, that's what this shows. V star V is I xi and xi xi are the same on M. And you can view V star V as an operator on M. Since the quadratic form is the same as that of the identity on M, it follows that restricted to M, V star V looks like the identity. That means V star V is equal to P. Let me say item. Identity M is really PM. They have the same quadratic form. So equal. Right? That means V star V is equal to fixes everything in M and it kills everything in M. Perp, that means V star V is nothing but PM. It is a projection on M, it is identity on M and it's 0 on M perp. i.e. V star V equals the projection on M. So we prove that 1 implies 2. Okay. And 2 implies 3 will be trivial because I want to prove that V equals V star V. V star V is a projection, that means V star V squared. That means V star I think I should have done it the other way. 1 implies 3 I should have done first.
By similar way, V star is also projection.
No, yeah, we will come to that in a minute. That's why we left a gap there. No, I should have, see actually what I've proved is, I'm being clumsy, I should have proved 1 implies 3 implies 2. See, if you know this fact, you multiply both things on the left by V star, you'll have this equation, which you say that V star V is a projection. Right? So 3 will trivially imply 2. This is 3 implies 2. So let me prove 1 implies 3. But that is what we've done. So we've shown that I want to prove that V because in this proof I proved that V star V equal to Pm. And V equals Vpm, because Pm is a projection onto the kernel of V. Right? M is a projection onto the kernel of V. So I organized the proof wrongly. I shouldn't have said I should have said let M equal to the kernel of V. And then that's what all this says. Assume M is the kernel of V. Sorry, M perp is what I was saying. Kernel of V perp. I'm assuming M is the kernel of V perp. That is the same as saying M perp is the kernel of V. And with just that notation to say that M is V, the partial isometry with the initial space M, is the same as saying that V star V is equal to Pm. We've argued here that 1 implies 2. And V is clearly equal to V times P. So V equal to V star V. Okay, if you think about it, there's nothing much in this. I'm just making a unnecessary fuss about this. I'm not saying it right. Okay, so I proved 1 implies 3 implies 2. Two implies 1 is clear. If V star V is a projection, That means it is a projection onto M. That means V will be isometric on M. Right? Two in place, one. So V star V is a projection, so it is a projection onto M. Now that means that I want to say that on M perp I want to say that V is 0. But that's clear from this, right? The kernel of M perp is the kernel of V star V. PM, which is kernel of V star V, which is the kernel of V. So I want to say the same thing again and again in a roundabout fashion. Okay, so I've proved that 1, 2 and 3 are equivalent, right? And now I want to say that this is the same as, if this holds, I just take adjoints in this equation. Maybe I should call it 3 prime. Or 3 star. Okay? But once I do this, then I can appeal to the earlier proved theorem for V star. V star satisfies this condition, and so V star is the projection, and V star is a partial isometry. Okay, and so now I can complete this family of definitions. I will say that the final space of V if you geometrically, if you think of V, the initial space as V, the final space is going to be where V maps. So this is going to be range of V. Right? But range V is closed because V is an isometry on its initial space. So this is equal to range V closure, which is equal to kernel perp of V star. Right? That means there is just the initial space of V star. V and the initial and final spaces for V and V star get toggled. If V is an isometry, then its adjoint is an inverse from its range to its domain. If V is a partial isometry, its adjoint will be a partial isometry which serves as an inverse from the final space of V to the initial space of V. Okay, so all these are fairly straightforward. So now let me come to the important theorem that involves partial isometry. Okay, this is the so-called polar decomposition. So, like for complex numbers, we have a Cartesian decomposition. You can write z as x1 by x2. And for operators, you can write operators as they have a Cartesian decomposition as x plus iy where x and y are self-adjoint. And for complex numbers, you have a polar decomposition, which is z equals e power a theta times r. I'll say it that way. These are non-commutative. So I like that version better. So I think of z as e power a theta times r. Number of modulus 1 times a positive thing. So actually in finite dimension, okay. So let me say this way. Let x be a weight. Unique decomposition x equal to v times a, where v a partial isometry, a positive. So this is an operator from each to k. This is in P of each. Positive means self-adjoint. It can't go between different spaces. So first you have a positive operator on each, and then you follow that up by a partial isometry. And finally, so he says it as, what do I say, V star V, that is the initial projection of V, is the support of A. Or another way of saying this, or equivalently, or I can write this equivalently as, the way I like to think of it as kernel of x equal to kernel of A equal to kernel of B. See, if V star V equal to S of A and V is the partial isometry, then the kernel of V is the same as the kernel of V star V. And that is the same as the support of A means it is the kernel of which I should say support of A of V star. Right? Huh? Support of A is vis-a-vis. Yeah. What I wrote first was vis-a-vis. Vis-a-vis is the support of A. But rather than getting confused with all this notation of L of A, and I like to think of this as saying, here is the Hilbert space H, here is the Hilbert space K, and there is an orthogonal decomposition here and an orthogonal decomposition here into two pieces. So this is the kernel of A, and this is the support of A, S of A, that is kernel of X, and this is kernel X perp. And the Hilbert space breaks up as orthogonal decomposition to kernel and kernel perp, and there is a partial isometry with this as the initial space. This is going to be V star. That is the range of V. I am confusing a projection and the range. This is the same as V, the range of V, which is V star, or the kernel range of X. And this will be kernel of X star. So what one is saying is that if you want to look at the operator X, if you look, so first there is a positive operator here, and you can see what the positive operator is not a mystery. In fact, A equals X star X power half. Which one, so one denotes this operator by mod X. Right? So this is kind of in keeping with our polar decomposition. Okay, so all the statement is more involved than the proof. The proof is very completely straightforward. It's a two-line thing. Okay, so let's see why all this is true. And then see later I'll come back and discuss why we're forced to look at partial isometries. The natural thing to have said when you wanted to have polar decomposition is VA where A is positive and V is unitary. But you cannot expect that in infinite dimensional Hilbert space. The whole problem is that, see, these two spaces must have the initial space of V and the final space of V must have the same dimension, because V is an isometry from here to there. So, now if B were unitary, that will mean that they are orthogonal complement, namely kernel of X and kernel of X star should have also had the same dimension. But in infinite dimensions, that is not true. You can take X as the unilateral shift. The kernel of X is 0, but the kernel of X star is one dimensional. So because, see, the unilateral shift is a classic example of it is an isometry. Its adjoint is a partial isometry. And it, because of such thing, see, in order to have this decomposition with this V being unitary, the kernel of X and kernel of X star must have the same dimension. If they are finite dimensions and they are in infinite dimensional space, there is no reason why those two should be the same. Okay, so after having said all that, let's quickly read the proof. The proof is really quite elementary, so what is involved? So I noticed that norm of xi square equals okay. This is xi which is x star x xi which is mod x squared xi. Mod x by definition is the positive square root of x star x. And so now I can write this as mod xi mod xi. That is norm xi is equal to norm of mod xi. So what have I said? I have said if I take if I look at the picture of my two eggs, if I take, this is the range of mod x, right? If I take any xi and look at mod xi or xi, the xi will be sitting somewhere here. Mod xi and xi have the same norm. So what we conclude from this is that, therefore, the mapping that sends mod xi to xi is a well-defined norm-preserving map from range mod x to range x. Right? Consequently, since this is well defined because norm-preserving. See, if we take something in the range of mod x, it can be written as mod xi and for different xi's. But this will say that if mod xi is, if xi, mod xi is also mod x theta, then xi and x theta must also, the difference have to be 0. That is, xi must be equal to x theta. So this is a well-defined map, and it is a norm-preserving map. Okay, and consequently, therefore, it extends. There exists an isometry let me call it V0 from range mod x closure to range x closure. Right? The mod x is a dense subspace of these are dense in these two, and you have a norm-preserving bijection between these two dense sets. So it extends uniquely to an isometry between these two spaces. And now, so I define V equal to define Vxi equal to V naught xi if xi is in range mod x and 0 for z in range mod x perp. You have an operator defined on a subspace, you extend it by defining it as 0 on the orthogonal complement. So then by definition, this V is a mapping which is 0 on if I call this space as M, then we see that V is a partial isometry with initial space V equal to M. Right, by definition, it kills M perp and it is isometric on M. And by definition, V of mod xi equal to xi for all xi. I V mod x is x. So V is a partial isometry, and further, what is its initial space? Its initial space is exactly the support of mod x. Right? So that's what I said before, right? Yeah, that A is going to be mod x. That means the kernel of V, kernel of C. So the polar decomposition is x equals V mod x. And the kernel of V equals kernel x equals kernel mod x by construction. That means I've satisfied all these three conditions that I wanted in the theorem. V is a partial isometry, mod x is positive, and they have this the three kernels are the same, and x equals V mod x. So now I just have to verify the uniqueness, which is also very quite straightforward. Why? So suppose x is also some ub, where u and b satisfy the same conditions. Suppose also as in polarity composition theory. That means u and b satisfy those hypotheses. But then I say then x star x will be b times b star, or b is equal to b star, b u star u b, because b is positive and hence self-adjoint. But what is u star u? U is the partial isometry. It is the projection onto the support of B. So that means it is the identity on the range of B. So u star ub is equal to B, so this is equal to B squared. But that means B is the positive operator whose square is equal to x star x. So with the uniqueness of positive square root, we conclude that B equal to mod x. But then we find that u and v, u mod x must be equal to x, which must be equal to Vb, which is V mod x. That means u and v agree on the range of mod x. And on the orthogonal complement of the range of mod x, u and v are both 0 by the assumption. Right? Therefore, hypothesis implies that u must be equal to v. So we have proved the uniqueness in the polarity composition. Okay, so let me read out this. Okay, and now if you look at the polarity composition, x equal to u mod x, right? If there is a polarity composition, is the polarity composition, of x, then you just take adjoints. What do you get? You get x star equal to mod x u star. Right? But as we just saw, u star u is the identity of the range of mod x. So I can write a u star u without any problem. But then I want you to observe that u star is a partial isometry. I want to say that u mod x u star is positive. Right? That's clear because mod x is positive. This is positive, this is a positive isometry. And what is the kernel of this chap? You can observe that they satisfy the same condition. That the kernel of this thing, this can be killed only if what happens?
Kernel of mod, kernel of norm.
So what is the kernel of U mod x U star? See, Xi is in here precisely when U mod x U star Xi this is positive. So U mod x U star Xi Xi is 0. So I am using the fact that if I have a positive operator B, then kernel of B, Xi is in kernel of B if and only if B Xi Xi is 0. Right? Because B Xi Xi equals 0 means that B to the half kills Xi. Right? That means if and only if U star Xi is in kernel of mod x. Right? If mod x U star Xi is 0, what is mod x U star? That is just x star. X star Xi is 0. If and only so Xi is in kernel of x star. And that is equal to kernel of U star, I want to say. U, if you take the polar decomposition, we look at that U, the final space is the initial space of the adjoint. So that means this decomposition satisfies the three requirements of the polar decomposition. That means this is the polar decomposition of x star. Therefore, in particular, U mod x U star must be mod of x star. Because if we take the polar decomposition of x star, the positive part will be mod of x star. So what is really happening is, let me go back to my Mutta picture. See, in this whole thing, mod x lives here. There is the support of mod x. There is the kernel of mod x or kernel x or whatever. So as far as mod x is concerned, it's a positive operator. It kills this space and is a one-one map of this space onto a dense subspace of this. And what this says is that this U see, this U can be thought of as a unitary from this piece to this piece. It's an isometry from this subspace onto this subspace. And what this says is that if you cut mod x down to its support, and if you cut mod x star down to its support, then the U can be thought of by giving a unitary operator which conjugates the mod x here to mod x star there. That is what we just showed says. U mod x U star is mod x star on that part. So U mod x U star is going to kill all of this, and U mod x U star is mod of x star. So U implements a unitary equivalence between mod x and mod x star. Between mod x restricted to its range support and mod x star. The partial isometry, when viewed appropriately, can be thought of as so this is like see, for example, if you have an operator x from C4 to C3, it will definitely have kernel because it's going to smaller dimension. It is going to have a zero eigenvalue. But if I look at the orthogonal complement of 0, that is on the support of mod x, which is away from the kernel of 0, that is the eigenvalue that it has there, that mod x has on that support, will be exactly the eigenvalues of mod x star on its support. So if mod x looks, so for example, if mod x is unitary equivalent to something like 2100, suppose this is a diagonal form of mod x, then the diagonal form of mod x star will be 2-1. You can say that with certainty. If you restrict this operator to its, barring the zero eigenvalue, the behavior of the two operators is the same. That is the only thing. Even the multiplicity, everything must agree. You have a unitary equivalence between these two. This is We'll do this now or? Okay. I'm doing a way to start. No, maybe I won't start something new at this stage. I think I'll just there's the lead. I had kept it away carefully somewhere. Huh? Thanks. Okay, so okay. Maybe I will make this noise. So see, if you take the unilateral shift, it's an operator on A2. What is its polar decomposition? What is mod U? Maybe not say U. Suppose S is the unilateral shift. Then what is mod S?
Square root of the S star S.
What is S star S?
That is identity operator.
So mod S is 1. So what is the polar decomposition? S equal to S times 1. That is the polar decomposition. And so this tells you why you have to have a partial isometry in the polar decomposition and not a unitary or isometry or anything. If you take U star, its polar decomposition, as we just saw, is going to be U star times the projection onto from the second vector onwards. And U star is going to be the projection onto the range. S star is going to be the projection onto the range of S closure. Range of S is already closed. So S star is going to be the projection onto everything, all the vectors for the second stage. So the polar decomposition of S star is going to be a star times that projection. And so here you actually have a partial isometry in the polar decomposition. Whereas for the unilateral shift you have an isometry. So you can't even hope to get away with an isometry. You can't have unitaries, you can't expect to have, you can, an operator can be written, in fact, let me just, make this obvious noise here. When I don't do paper, if an operator can be written at all, if you can write X as UA, where U is unitary, if you have any operator with this decomposition, then exactly as in the proof of the polar decomposition, uniqueness of the polar decomposition, you can see that A has to be mod X. Because X star X will, that U star U will get killed, will give you exactly A squared, and with A positive. A will have to be mod X and so I want to say that, and what is X star? I can write the same thing that I wrote before. U star, UA U star. So what I'm trying to say is that if at all you have such a decomposition, and if this is the egg that you have for X, so this is the support of mod X, this is the kernel of X. If at all you have such a decomposition, this U must necessarily map the support of mod X to and this okay, let me give this as an exercise. Okay, so what am I saying? I'm saying that X can be written, X has a decomposition X equal to UA, where U is positive, unitary and A is positive. I want to say if and only if kernel X and kernel X star have the same dimension. So what I want to say is that if you take the usual polar decomposition, if these two have the same decomposition, then the polar part, that U will give you a unitary of one piece onto another piece there, and the complements have the same dimension, means you can take any unitary from that space to that space, they have the same dimension. So if this happens, then you do have such a decomposition. Conversely, if you have such a decomposition, then you can see that kernel of X, it's trivial to see that something X kills something if and only if X star kills U of that. That is, U must map the kernel of X onto the kernel of X star. And U is unitary on the whole space, so that those two must be same dimension. So because you are in infinite dimensions and these two things may not have the same dimension, that is why this whole thing comes about. And
here X equals to UA in the polar decomposition if U is unitary.
No. I'm saying not in polar decomposition. An operator X can be written as a unitary times a positive. I'm saying if and only if kernel and kernel of x and x star must have the same dimension. In which case that U will be something which restricted to the support of mod x will be the polar part of x, and on the orthogonal complement it maps the complement to the support mod x star perp. Okay, so we'll try. See, this is to prove most theorems about operators. What one does is see first how you can prove it for self-adjoint operators, or better still for positive operators, and then try to use the polar decomposition to get to any operator. So, okay.